Hi everyone, I am Miguel Zamora, and in this video I will present our work titled Learning Solution Manifolds for Control Problems via Energy Minimization. Optimization-based control is a key element in the motion pipeline of today's most advanced robots. Optimization-based control can deal with highly nonlinear problems that range from simple inverse kinematics problems to full-blown trajectory optimization. However, optimization algorithms are still generally too demanding for some real-time applications. One possible approach to speed up optimization-based control is to generate a dataset of solutions in an offline stage for different conditions, and distill the dataset into high-capacity approximators like neural networks that can be queried in real time. Here, we note that our focus is on training trajectory policies for problems that can be formulated as one-shot decision-making problems. That is, policies that given some input parameters p, output entire sequences of actions. Consider the example of numerically solving the inverse kinematics problems of a two-link planar mechanism. Using behavioral cloning to learn the solution of space of such simple problem leads to a poor performing policy. We attribute such poor performance to multimodality, as almost every Cartesian target admits two or more solutions. Multimodality is a common feature in many robotics applications, like collision avoidance, where a robot needs to reach a point while avoiding an obstacle. The energy landscape on the left is the result of evaluating the position error on the entire workspace of the two-link mechanism for a policy trained by a behavioral cloning. If we overlay the samples that were used for training and we zoom in, we note that high energy regions in red are surrounded by multimodal solutions A and C, which constitute conflicting samples. In contrast, our method produces smoother and more consistent landscapes using different sampling strategies. Our method is a gradient-based approach to distill trajectory-based policies, and we evaluate it in a series of inverse kinematics and kinematic trajectory optimization problems of increasing complexity. Given a set of input parameters p that describe a single instance of the problem, a trajectory policy pi, and a state trajectory s bar that depends on the input parameters and on the action trajectory that pi produces, we can define an energy function that encodes the goal of the control task. We then formulate the training process as the minimization of the integral of the energy over the space of input parameters. Such integral can be approximated by a Monte Carlo integration using a finite sum of random samples of the input parameters p, for which we can obtain a first-order update rule in the parameter space theta. We can reinterpret such optimization process as a sequence of behavioral cloning steps from a convergence supervisor. Considering the behavioral cloning loss L, we can show that by evaluating the target Tm numerically and feeding it to a behavioral cloning loss, the resulting update rule is equivalent to minimizing directly the energy in parameter space. Using similar targets T allows us to incorporate second-order information and enables the use of line search techniques. We refer the viewer to the paper for more details. Using this reformulation together with a fixed set of samples from the input parameters already results in more uniform solution landscapes. However, to address actively conflicting solutions, we introduce a rejection sampling strategy, which consists in choosing a seed sample P0. We then grow the training set by adding samples P1, P2, and so on that are close to the seed sample. We compute dynamic targets Tm for each sample P, and we remove the conflicting samples from the training set based on a similarity metric D. We iterate these steps, growing the training set further. The landscape on the right shows how this rejection sampling strategy leads to smoother solution manifolds. We compare our approach using different sampling strategies against behavioral cloning and Dagger. Here, the evolution of the energy landscapes for a 5-link planar robot showcases that our conflict detection mechanism is effective and that policies trained with our method are better performing. Furthermore, we compare against implicit behavioral cloning, which has shown great results in multimodal settings. While our method is not able to preserve multimodal solutions, we perform better in terms of position error and compute time. Moreover, we use our trained policies to warm start 1,000 different kinematic trajectory optimization problems, which led to a speed up in computation time while obtaining low position and orientation errors on average. Our method can also be applied to a variety of simulated physical systems, like point masses and rigid bodies moving on frictional floors, or rigid bodies connected by flexible attachments. Furthermore, we can deal with variations of the physical properties of the system to be manipulated by including such properties in the input parameters. Finally, we believe that this work, with all its exciting future avenues of research, sets a good starting point to enable robust and instantaneous queries from well-established optimization-based control algorithms. Thanks for your attention.